Hello and welcome to the Geek Nighter podcast. I'm your host, Kaival Yapte, and I'm thrilled to have you join us. So today we are diving deep into the database called TiDB, and I have Lee from PingCap, the company behind TiDB.
Yeah.
So welcome, Lee. I'm really excited to have you today and also excited to dive deep into the world of TiDB and how it works. So why don't you start with a little bit of introduction about yourself and about PingCap?
Yeah. Yeah, sure. Thanks, KV, for having me here. I'm Li Shen from PingCap. You can just call me Li. And I'm the second employee of PingCap, also in the founding engineering team.
Mhm.
So I joined the TiDB product team at the very beginning. And also I know our store engine, TiDB, a whole bunch of things. And for PingCap, we already in this area, the database area for more than 80 years. It looks like a long time for a company, but it's still not very long for a database company. We focus on the single product TiDB, a distributed transactional database, but we also have some TiFlash support some of the analytical workload. So there's just there's a bunch of components there, and we can talk more detail today. Yeah.
Absolutely. Yeah. Thanks for joining and thanks for the introduction. I'm also curious about the name PingCap, as we were talking about right before recording this. The cap in the PingCap is basically referring to the cap theorem. So talk a little bit about that.
Yeah, you are right. Correct. So the name our company is PingCap. The cap is exactly the CAP theorem, and the ping is the network command. That means we are going to reach the CAP theorem a little bit, and so that's the idea behind the name. So we are building the distributed system, and we try to achieve the CAP. Actually, the name of TiDB is also interesting. The TI stands for titanium, and that means the database is solid. It's more than rock solid.
Hmm.
So we want to build a reliable database.
Awesome. Yeah. That's really good to know. And it's really interesting. Cool. So I think you've briefly described that. It's interesting that you mainly mentioned that it's a transactional database, but you also support some of the
Yeah,
analytical use cases. So we'll
yeah,
go deep into how it is done actually. But I want to add more details there. If you have to define TiDB, would you say it's a like primarily transactional database, or it's so people say hybrid model, right? Like it's a hybrid of
yeah,
both worlds. How would you define TiDB in that sense?
yeah. I actually early we call it a distributed SQL database, and it's a primary transaction database because most of the time people use TiDB for their workload for their online application. And I think for an analytical workload or analytical product, probably for the data warehouse or data lakes, most of the time people use that for the offline systems. So TiDB stand more on the online part, and we have some features like support some of the analytical workload because we have the observation that in the modern applications, the the boundary between transaction and or the simple workload and the analytical workload is blurred. And there's, for example, for the SaaS application, their data plane or control plane, there's not only just simple point get insert, but there's also some kind of aggregation or simple join support some real-time insight for their application. You can see some real-time dashboard in the SaaS backend. I think the requirement from the application change a little bit along the days. And so that's put more requirement on the database side to support those changes. So that's why we want the database easy to use for developer. They do not need to set up a separate environment to support their need. And they can get benefit from the probably enhanced computing capability from the single database.
Interesting. Yeah, that makes sense. So basically, the idea is to support both use cases while abstracting away the complexity of maintaining two databases. While you
Yeah.
just have one database and support both workloads, but primarily you want to have like online transactional workloads, right? That's the understanding.
Yeah.
Okay. Okay.
Yeah, that's a primary use case of TiDB for online transactional workload.
Interesting. I was thinking a bit about API, and it says it's like MySQL compatible. And some of the other distributed SQL or databases that we have, they focused more on the Postgres compatibility.
Yeah,
Talk a
right.
little bit about that. Did you also consider Postgres compatibility, or did you always focus on MySQL compatibility?
Yeah, actually, for now, we still focus on the MySQL compatibility. And to be compatible with Postgres is a huge project. And
Yeah.
that's not only the protocol and the syntax, but also the behavior of the database.
Yeah.
So it's a huge project, and we still stick on the MySQL part for now.
Okay. So it's totally compatible with MySQL on the API side, right?
Yeah, so for the API, the protocol syntax, and also the behavior.
Hmm.
And I think there's still a large portion of the market of MySQL.
Okay. Interesting. Cool. Just to talk about a little bit more on the types of use cases that TiDB can be used for. What are the primary use cases that you have seen company using TiDB where they wanted to solve some problem that they had with their existing databases? So give us if you have some examples there.
For the use case wise, our primary use case is still the transactional workload.
Hmm.
And when people have issue of the scalability or reliability of their relational database, MySQL or sometimes Postgres, Oracle,
Hmm.
they may looking for new solutions. Type is one of the candidate solution, and we help them to scale their database. And because TiDB is MySQL compatible, so it's very easy for MySQL user to migrate their data and also application to TiDB. And we provide a bunch of tools for that. One of the main use cases scale or replace MySQL
Hmm.
or MySQL-like database like Aurora MySQL or MariaDB. So we can help them to scale probably up to 1 petabyte the data volume, million of QPS, and support their business growth. And also some of the companies, especially in the financial sector, they care about the reliability very much. And next SLA and TiDB have built-in high availability and a bunch of DR solutions. So gives them peace of mind about the reliability of database. That's the first kind of use case. Still, it's a bigger and better relational database for your mission critical transactional workload. And since TiDB can scale to a large, traffic data, and some users found that they can put multiple applications on single database, consolidate those database instances into a single cluster. So in this way, they can reduce the cost of both operation and also the hardware cost. Maintaining hundreds of databases
Mm.
is much harder than maintain one TiDB cluster. So that's another use case, just consolidate multiple database instances into single cluster. And that's the second one. The third one, I would say sometimes I think there are some application built on top of the data. We can call it the data as a service architecture. They just grab data from somewhere,
Hmm.
upstream data sources, like customer 360. So they get data from upstream data sources
Hmm.
and consolidate data there and build the data application there. So it's like data as a service architecture. In this architecture, they need a storage that can scale, can do the fast ingestion because data volume could be huge. And also they want real time the data as fresh as possible. Then the server layer can be there's high concurrency query there. So that means they also need database can support high concurrency query. So TiDB is a good fit for this kind of scenario. So that's the three main top use case for TiDB.
Yeah, very, very interesting. And so it takes away some of the problems or bottlenecks from traditional MySQL deployment and has this highly available, highly scalable, and reliable
Yeah.
infrastructure that there's less pain to manage in a reliable manner. So that's the
Yeah.
primary
Yeah.
use case.
Yeah. That's a primary use case.
Okay,
Yeah.
interesting. Cool. So I think this is clear. What are we talking about? What TiDB would bring to us? Now let's talk about the how part, right? So to
Yeah.
do that, let's start with how, when I ingest some of the data. So it's typically, let's say, transactional workload, right? There's a e-commerce application and I have some orders, and I just take this example always because everyone is aware of e-commerce use case. So I have orders being created. So I have some orders data And take us through the API layer from when the data is ingested into TiDB and how it reaches, how it routes to a different node, and up to the storage layer, how the data flows.
Yeah, sure. Yeah, for the red path, I can describe a little bit. The first layer for the application is our MySQL layer, MySQL API. So the application will use MySQL API. You can use any of MySQL driver or connector to connect to the database, then send the SQL command to TiDB. For example, you insert one record into TiDB. So you just send insert statement to TiDB. Then our SQL layer, we also call it TiDB node, will get data, get the SQL command. Then it will do the passing, the planning there, and convert for the insert statement, our SQL layer will convert the record into key value pairs. And the underlying storage engine, TiDB, is a key value storage engine, which supports transaction. The SQL layer will convert the record into key, and also the index into key value pairs, because it knows the schema of that table, and if there's any index on the table, according to the schema, it will convert the data into key value pairs and call the key value API of TiDB to insert data into TiDB. And the process of writing data into TiDB supports transaction. So the TiDB will call the transaction API, begin like the commit those transaction API or key value set or get API to interact with TiDB. For the write path, TiDB will send the key value pair to a TiDB node. And which node to write data, it depends on the routing information, primarily stored in PD, another component. That's PD stands for placement driver. So TiDB can get the routing information from PD and send the data to a certain TiDB node. But getting the routing information is not necessary for all times, because TiDB specifically can catch the routing information. So most of the times, TiDB do not need to consult PD. And TiDB sends the key value write command to TiDB node. On TiDB, we use RocksDB as underlying storage engine to process data to disk. And on top of RocksDB, there's rough layer. We do the replication between the node. And also there's a transaction layer and also API layer. And TiDB got the key value set command. The rough leader will get that requirement. Then it will replicate the data to the followers. For a consensus group, there's by default three members there. One is leader, another two are followers. The rough will guarantee the strong consistency between the replicas. So for a single replica, it will process the rough command and process the rough log to the rough log engine, then try to apply the rough log, which is the key value data into RocksDB, and then RocksDB will process data to the disk. Yeah. So that's a basic process from SQL layer to the key value layer, transaction, raft, and also DB.
Interesting. Yeah. So it looks, so just to validate my understanding, so you have the query layer or the query processing layer where you process the SQL commands and try to send it to TiDB, where it is actually converted into a key value pair. So my relation, basically, if I have a table, let's say the orders table, and I have order details. So each of the row will be converted into multiple key value pairs is what I understand.
Right? For each record or each row, there's at least one key value pair for the record. And if there's an index there, second index there will be an extra key value for that record.
Got it. So if I have, let's say, an order ID column, customer ID column in the orders table, and I also have the orders value, let's say total amount and some other information, right? So how would that map to a key value? Can you talk a little bit about that?
Yeah. So for the record, it's simple. We use the primary key or row ID as and encoded in, and also there's a unique ID for each table. And also there are certain prefix for record. So we combine those together and encode it into a key, a byte array. Then we put all the columns into the value part. And that's for record. For the index, we will encode the index column value into the key part and also the primary key as a value part. So the index is like a pointer to the record. So
Okay.
when you look up through index, you get the primary key or the row ID, then you can get the key of the record.
Okay. So it's still one row or one tuple in MySQL table format. It will map to one key value pair, right? Because all the columns are in one value, or they.
Yeah,
Okay.
exactly.
Okay.
You want one value.
Okay.
Yeah.
Okay. Interesting. So there's a specific ID for a table. You map it, append it with some column or sorry, row identifier
Yeah.
or the primary key, which is, let's say, order ID in this case. And then the value is basically all the column values, right?
Yeah, exactly.
Okay.
One more comment for the encoding part, for the key encoding, we apply a mechanism called memory comparable encoding algorithm. That means we do not need to decode the key to compare two keys.
Okay.
So in this way, the key stored in TiDB in the order of their original order, we encode into byte array, and we do not need to compare the two keys. But we do not need to decode it first, then do the comparison.
Okay.
So that means we can scan the key range in the order of their original value. So it's good to do some like filtering.
Interesting. So it's pretty standard in a way that how other databases also work. Okay, interesting. Cool. So I think I have a good understanding of how the data from the API reaches the storage node and how the storage node is picked up. This is good. And I want to talk a little bit about the index part. So you mentioned that, so let's say my primary key is order ID in this case. And how does the ordering of this work? So you mentioned you use an algorithm to avoid decoding the key.
Yeah.
And so you can directly compare it. And also scans are easier then. So let's talk a little bit about that, like how the key value pairs are actually ordered. So the scans are done in an efficient manner.
Yeah. Actually, logically, TiDB is a big ordered key value map. They are ordered by the key, and for then in the key space, we will divide it into small chunks. For each chunk, it's physically the data set of each chunk is less than 96 megabyte, and for the whole picture is ordered, and for the key value, for the key in each chunk, it's also ordered. And for the order, the key and also the value are byte arrays. And for the order, you can just compare each bit of in the byte array. And I mentioned that we have so-called memory comparable algorithm. That means, for example, for each type of data, the integer, date time, and others, we have an encoding algorithm for each type of data. And for example, probably date time, you can compare two value of date time according to their value. Then with our algorithm, you encode those two values into byte array. So the result of comparing the two byte array is the same as comparing the original value of the date time. So in this way, when we encode the data, no matter index or primary key or single index, the key is ordered as their original value.
Okay.
So in this way, we can scan a ring. For example, you want to query the people which the age is greater than probably 40. You can just encode the 40 with some information schema, then compose a key, then seek in the key value, in the key range to a place that the value should be greater than 40. Then you can use the next to get all the value there.
Interesting. Cool. So I think it's also important to consider what kind of queries you're going to perform on this model.
Yeah.
And that's how you would try to model your data and also your keys. So when I say create new index, let's say I want to have all the orders that a customer has placed in a time ordered manner, how would the key look like? So should I encode the customer ID as well in the key along with the timestamp, or how would that work?
Yeah, so actually the schema depends on your workload, your query. how you like to query data.
Yeah.
For example, the primary key is order ID, and you have the customer ID or customer name also in the table,
Mhm.
and you want to query the data through customer ID, right? In this scenario, you can create a second index on this table, probably just customer ID.
Yeah.
But if there's other queries, like you want to query the customer order in a certain day or certain hour, probably you can use customer ID as the first call. You can create a composed index and put the customer ID at the first place, then the data, the date,
Yeah.
or the time for the order. Let's say just you want to query data through customer ID, then you have second index just on customer ID. Then for each record, we will have key value pair for the customer ID to the primary key. Then all the data, because the TiDB, the data is ordered with the key, and all the data for that index will sit together, and you can just sit to a place in the key space, then use next to get all the data with the same value of the customer ID you given in the query. So in this way, you can get all the primary key for that customer. Then use that primary key. Primary keys. You can get all the record for that customer. So that's the basic idea for that. For composite index, it's more complex. You need to take care of the order of the columns in the second index. It matters.
Okay. Yeah, that makes sense. And that's the reason understanding your workload and what kind of queries you want to optimize for is also very important, because that can impact the way you write and then eventually what you read. Cool. That makes sense. Since we talked about the two types of workloads, transactional and analytical. So let's say, this was the transactional use case, right? Where I'm creating an order and it's getting persisted.
Yeah.
Now, let's say if I also want to enable some kind of analytics, let's say like more complex analytics where I am trying to join some of the multiple data streams and then perform analytics on top of it. So when I'm creating an order, I am also, let's say, analyzing some other data related to the customer, let's say the click events or something like that. And I have the data coming in from a stream, let's say from Kafka or something, and I'm trying to ingest into TiDB. And how would I have the data in one place such that it works for the old use case, which is the transactional, and also the analytical use case? So how do I enable that analytical workload now?
Yeah. So talk about the analytical workload. It's in TiDB, there's a lot of mechanism to support that. First, I mentioned there's key value API in TiDB. There's also a processor API. SQL node can push down some of the operators into TiDB. You can just push down like the table scan, the filter, index scan, partial aggregation to TiDB. And in this way, TiDB can pull some of the data in advance, do not need to return all the data to the SQL node. And so this is like a distributed computing framework. You can, because if the data volume is large, the data involved in the computing for a certain query is large. The compute task will distribute it into multiple TiDB node. And there they can accelerate the computing distributed manner. And inside the SQL node, TiDB, we can also use multiple threads to process one query. For example, you mentioned join, we support multiple join algorithms like hash join, indexing graph join, and the sort merge join. So it depends on the schema and the query. The planner will choose which is best way to do the join. And there, for those operators, most of them are also multi-thread operator that we can leverage the modern CPU to accelerate the computing. And we also have some optimizations for the large data volume computing. For example, in the SQL node and also the TiDB node, where we have vectorized computing engine. That means if the data volume is large, it can be very fast. It's already a parallelized and vectorized distributed for computing framework in both SQL node and TiDB. And we also have a columnary extension for TiDB. We call it TiFlash. The flash means it's fast.
Fast, yeah.
And TiDB is basically a role-based store engine, and the TiFlash is a column-based store engine. the data will be replicated from TiDB to type flash through Raft. The type flash node will act as a Raft learner to replicate data from TiDB. So it's a learner. So that means for the Raft purpose, for a certain log or certain write, the learner will not vote for the write. So the TiDB will not wait for type flash if it is slow to write. So that will not slow down the TP workload. And type flash will convert the data from row format to column format and store it into local store engine. It can support very high concurrency write or update compared with other columnar store engine. It can support high concurrency update or in-place update and auto write because it's just for the data in flight. It just stores the data in memory. And then it can serve the query. So there's maybe case it just stores data in memory, but the data crash, the data will lost. But since we still have 3 replicas in TiDB part, it can still get the latest rough log from the TiDB and rebuild the data. So there's no concern about the data consistency. So the data is replicated to the type node, so Raft as a learner. So it's like async replication. But that's the right part. For the read part, actually, by default, type flash can still provide a strong consistency with row storage because by default, type flash will check the rough log index with the leader to see whether I have the latest data. If I do not have latest data, I can wait for a while. But you can change the default behavior to get what type of data you have right now. It's async, but still provides strong consistency for a certain row store. That means for a single query, you can leverage both row store and the column store to do the computing. Do not worry about the consistency. And the planner will decide which storage engine to go for a certain operator.
Interesting. Yeah. Basically, to support the analytical use cases, you want your data to be in columnar format because that is the standard way of doing it. And it also enables better analytics and faster analytics as compared to row level, because analytics is typically done on one column. And for transactional use cases, you want the entire row. So that makes sense. So basically, you have two storage for one type of data. So now the order is also being stored in key value format and also in columnar format. And the way it is done is it is replicated uh, through to the type flash database, which is a columnar store, and it acts as a Raft learner, right? So again, it's an asynchronous application, as you mentioned. I want to understand how the consistency model works. So let's say since it's asynchronous and someone is running an analytical query, how would the consistency be guaranteed? So you mentioned that it will check the Raft log and understand if it's running behind or it's already updated. And what happens when it is running behind? Will it wait until the Raft log has been up to the point?
Yeah. For by default, we'll check with the leader to see whether it has the latest data. And if it's running behind, it will wait for the latest rough log and apply the logs there.
Interesting. And what does type flash use for the storage layer?
Oh, actually, 3 years ago, we built the type flash project based on the code base of ClickHouse. We leverage some of the functionality like computing engine, but we rebuilt it store engine because I mentioned we need to support high concurrency insert and update. That's not the same kind of workload with ClickHouse or with other column store engine. So we built a store engine called merge tree, which means the data is the changing part. The insert update, we store the change, the modification in memory. And there is also the old data we will store on disk. Then when it reads data, we will merge the data and the data on the disk to get the latest data for the query. Yeah. So we have a new engine called data merge tree and to store data.
Interesting. Yeah. Okay. And so it's interesting because many of the analytical systems, they try to support updates and deletes, but in a different way. So
Yeah.
they have this tombstone records and it happens eventually, but they don't allow, let's say, in-place updates. So what was the use case
Yeah.
where you wanted to support in-place updates as well?
Yeah. Actually, TiDB can be only used with TiDB together, and you cannot use TiDB standalone. And so you can just see TiDB as a special index for a certain table, and you just create a TiDB node, or you use DDL to change the schema of the table to have an extra TiDB replica for data. It's an extension for the ORTP workload. So that means, yeah, the data will be read into TiDB first, then replicated to TiDB. And our private workload is still the transaction workload. So for transaction workload, there's always like the high concurrency or in-place update. And so TiDB is optimized or designed for this kind of workload. For other workload like append only, store the logs or time series data, we can still do that. But the performance may be not comparable with some purpose-built time series database. So our primary workload is still transaction workload, and we built TiDB to extend the capability for some of the analytical workload.
Interesting. Yeah,
Yeah.
I understand, like when you mentioned it's more on the transactional side, but it also supports the analytical use cases. So basically the analytical use cases, performance wise, it might not be up to the speed as some of the specialized analytical systems, for example, ClickHouse or Pachepino. Is that
Yeah.
right to say?
Yeah. Yeah, that's right.
Okay. And
Yeah. Because they are
okay,
optimized
but
for analytical workload.
got it. Basically, people get it for free. While having a transactional database, you also get analytical store. Of course, there is going to be some trade-offs, but that makes sense. And the write path is pretty clear. I know we also touched a bit on the read path, like how indexes are created and how scans would be done. Let's talk a little bit on the read path. I know it is going to be very similar because again,
Yeah.
you have a key where you're reading and you have to go to the node. But let's try to dive deep into that and also focus a little bit on how the caching part is used to avoid the call to placement driver.
Yeah, sure. For the read parts, and it's simple. Basic idea is that the planner will do the query planning to the best query plan or the most optimized query plan, and execution engine will convert the plan into some of the operations on a certain key range. Yeah, we already encode the data into key value pairs. And for example, you have the example we mentioned before, you want to query the data for a certain customer, and you have index on the customer ID. Then the operation will be probably there's another filter besides the customer ID, and we can also add an aggregation there to account. So basically, the planner will decide we will use the index on customer ID to do the filter first. Then we can push down the index scan into TiDB, and the TiDB node will scan those key rings and get the primary key and return back to the SQL node. Then the SQL node has the primary key for the record. You may interest in a particular column in those record. Then the SQL node will use the primary key and build the key value operations to the compute task on those key value pairs, then push down the key get and also the filter. There's maybe another filter in the where condition to TiDB. And also we can prune the column. So we take the SQL node, then send those computing tasks to the TiDB. And there they can do the further computing and return the result back. So just choose the best query plan and decide the key range to execute those query plan and send the computing task to the TiDB, hold those key ranges. That consult in this process may consult the PD, and the SQL node will get the result back and do the final aggregation and return the result back to application.
Interesting. You mentioned a bit on how you push down the filters to the TiKV node. This basically avoids the additional data transfer, and the pruning can be done on the node itself.
Yeah.
So only the relevant
Yeah.
data will be sent back.
Yes, exactly. For example, if there's aggregation, we can push down the partial aggregation to the TiKV node. For example, for the count for each node, or for each region, just need to return an integer to TiDB, and single node will add them together, get the final aggregation result.
Interesting. I think this makes sense. How would it distinguish between the analytical query and the transactional query? So let's say so from the user perspective, is it like two different interfaces, or it's just depending on the query, it is routed accordingly to the column store versus the row store?
Yeah, there's single entry for user for all the queries.
Yeah.
They do not need to distinguish the simple query or a little query, just send query
Yeah.
to TiDB, and the planner will choose which store engine to go for a certain query. And it can also use multiple engine for a specific query. For example, that query which need to do the full table scan. Then after the full table scan, there's a join. The join, probably the join, we can choose the index lookup join, which can leverage the index in the row store engine.
Yeah.
So the planner can push down the full table scan to the tab fetch node and get the result back. Then use the TiKV for the index lookup join. Then build the final result. That's easier
So
for a developer.
that makes sense. So I've tried to wonder. So basic analytics can still be done from the transactional store, right? Let's say you say like select count star for a given customer ID. So that is still
Yeah.
like an analytical style query, but it still can be performed very well on a transactional database, right?
Yeah,
If you have
actually,
the right kind of index.
yeah, it depends on the cost. The,
Yeah.
the planner will estimate the cost and decide which way to
Okay.
go. For maybe the distribution of a certain column is not even, right? So there's a customer with large volume of
Yes.
data. So in that case, the planner, the SQL node may decide, okay, we will ignore the index, just go to the tab fetch to scan all the table. Yeah, depends on the cost.
Interesting. Cool. So I think the write path and read part is pretty clear, like how it reaches the analytical store versus the transactional store, and write path is also very interesting. Let's talk a little bit about the high reliability part. Like how do we ensure that
Yeah.
the system is reliable? You also mentioned you have a chaos testing tool. So let's talk a little bit about that, like how that is leveraged to test the database for reliability.
Yeah. Yeah. Okay. Yeah, I think one pain point for a lot of DBA or infrastructure engineers is that how to maintain the reliability of their service, right? Basically, for most of the production environment, people will set the primary, secondary replication for their database. And for TiDB, we have a bunch of tools to guarantee the reliability or high availability. And in TiDB, in TiKV, we already talked about the Raft. We do the replication automatically. And with Raft, we can do the replication with strong consistency. And in this way, we have multiple copies for each piece of data, right? So
Yeah.
when there's like a failure of node, no matter it's memory issue or network issue, one node gone, and the followers on other node will detect that instant because there's no heartbeat from the leader, and the two two node align will do the re-election and
Yeah.
choose a new leader to keep serving. And for if the node gone for a long time, that may be a short term issue because you are doing like a rolling upgrade. But if there's a
Hmm.
long-term issue, the PD will decide to rebuild the replica failing node. Yeah, with the replica alive on other node. So in this way, the cluster can auto healing from the failure automatically, both short term and long term. So that's a basic idea for the high availability. And besides TiKV, for both PD and TiDB, there's also multiple instances for PD and TiDB. So there's also auto failover for those components. So it's for the whole architecture, we have the auto failover mechanism. That's a basic idea of the availability. And for the database, we support some features. For example, similar with MySQL, binlog, we have a component called TiCTC. CTC stands for change data capture. So it's similar with MySQL binlog. So you can set up primary and secondary cluster to do the replication as a read-only or standby cluster there. And we also have support backup and restore. It's a distributed manner to do the backup and restore. It's fast. And also we have PITR fetchback bunch of mechanism there to support your HADR plan. Yeah. So that's there's one more thing. There's at least by default, there's 3 replica for each piece of data. And the placement of those replicas are critical to handle the node failure. We will consider the location of the takeaway node to place those data. You can just add labels to the takeaway node, no matter it's a reg or zone or region. And the PD will try to not place multiple copies in a single place. In this way, we can handle the failure of single node or single zone.
Makes sense. So basically, as a database admin, I have the control of how much or what kind of fault tolerance do I need. Do I worry about the data being in the same region, same rack, same zone? So I can decide. And why? So what is the trade-off here? So when I decide, okay, let's make it in different zones versus different racks. So I guess is cost the only thing, or there is more trade-off to it?
Yeah, so I think primary consideration should be how much do you care about data. By default, we have 3 replicas, and there I also see some production use cases. People have 5 replicas for their data because those data are super important. They need extra storage and machine to run those nodes. And talk about the cross zone or even cross region deployment. You need to provide better support from the network part. There's maybe extra cost for the cross zone or cross region of the network transfer.
Yeah. So basically, I have to consider how important is the data and also consider the cost. And I guess since the writes are providing me high consistency and it is making sure that the replicas are also up to date, having this setting is also important. Otherwise, writes might be impacted.
Yeah. Yes. Exactly.
Okay. That makes sense. Cool. I think it's a very interesting, like auto healing ability of the database to create new replicas whenever there are problems. Let's talk about some of the considerations when it comes to, let's say, the migration part, right? So let's say I'm currently using MySQL or some other database, let's say Postgres. When should I start thinking about moving to something like TiDB? So you mentioned that people, when they face some issues with, let's say, the scalability or the reliability of their MySQL cluster, they want to consider TiDB, right? What about the other databases? Is it, since MySQL is easier because it's a MySQL compatible database, but what happens if I have, let's say, Postgres or something else? How would the migration look like, and what things I should keep in mind?
Yeah. First, I think we can talk about what's the reason people migrate to TiDB, no matter it's from Postgres, MySQL. So basically, I think I still see a lot of cases people migrate from Postgres or Oracle or DB2 to TiDB, even there's no compatibility of those databases. So people just looking for a scalable transactional database, and there's not many good options. TiDB is one of them with scalability and reliability. And it's better than it has built-in features to scale or to do auto failover. So give the DBA peace of mind. And also, I have seen some use cases people migrate from HBase or other NoSQL system into TiDB. They choose HBase because it can scale. Their data volume is huge, and they also want a system can do the auto healing for their online services. So they choose HBase. But but they realize that their developer actually needs the SQL to query the data there, not only the simple key value lookup, but they also want like a certain index and to access their data. It gives more flexibility to their developer build their application. Compare with operate the data with low-level key-value API, it's better or more productive to with the SQL API. For example, Pinterest, they migrate their database to TiDB because they actually need the second index to access their data. Before TiDB, they built a few systems around HBase to provide the functionality like the second index. And that's the requirement from their application. So when they need scale and high availability, they may choose NoSQL systems. But actually, the SQL can provide the productivity of their developer. So those cases, TiDB is a better solution. It's more modern solution. So that's the driver or the motivation why people migrate from the single node relational database or some NoSQL system into TiDB. And for the migration, MySQL is simple. We provide a bunch of tools, like we support the MySQL backup file from MySQL dump, from my dumper or MySQL dump, and load it into TiDB. We also support with the backup of AWS Azure MySQL in S3 in Parquet format, and load the backup into TiDB directly. And for the data ingestion into TiDB, for the full data loading, it actually in a lot of cases, we will load a few hundred gigabyte or even hundreds of terabytes data into TiDB. We have a tool that can convert the data into the format of TiKV, the underlying storage directly. So that's not a logical ingestion with insert, but a physical ingestion from the backup file to the RuxB file and ingest the file into RuxB. That's much faster than the insert statement. And we also support read the bin log from MySQL. In this way, we can do the incremental migration. And you can also set up a TiDB as the stand-up cluster for MySQL. So for MySQL, it's easy. And we can do the full migration and also the incremental migration. And for other databases, usually the user will dump data into CSV file from other databases. I think most databases can do that. And then our data ingestion tool, we call it TiDB Lightning. TiDB Lightning can read the CSV file and convert it into RuxB SST file directly and ingest into TiDB. So in this way, we can do the migration from other databases.
Yeah, that looks like there is a very standard way of migrating from different databases.
Yeah.
Let's have a little comparison between, TiDB and other distributed SQL databases. So there is, for example, YugaByteDB or CockroachDB. What is the let's say the selling factor of TiDB? Like one is definitely if you're using MySQL and you want something MySQL compatible, TiDB is a great option for you. Where CockroachDB and YugaByteDB, they focus more on the Postgres compatibility. The other part which I see is the analytical use case where let's say if the customer or the user has some analytical use case on top as well, and they think that TiDB can be a great use case. So that is another, let's say, a selling point. What are some of the other features that TiDB supports where users will find more suitable workloads when hosted on TiDB as compared to other distributed SQL databases?
Yeah, that's a good question. You already mentioned the Postgres and MySQL. That's one differentiation from between TiDB and those two products. I think TiDB is probably the only options for MySQL compatible distributed system. Distributed SQL database, probably the only option there. So that's first one, the protocol layer. And for you also mentioned we can do both the transactional and big workload. And for some applications, I think that's good to build their application if they need those capability, like the SaaS backend, like some data service application. And so that's another thing. And the third thing I think it's open source. YugaByteDB is also open source, but CoreDB, I think it's source code available. I think it's still debatable if they are open source license. And for TiDB, our kernel, our main tools I mentioned, like the TiDB Lightning and TiFlash, those are all open source. You can get it from the community. I think for a large account or large enterprises, they care about open source.
Yeah.
Right. So they can avoid like the vendor lock-in, or there's more innovations in the more active open source community. Then another thing in my mind is that we focus on the transactional code, and we focus more on the single region, scalable, reliable database. We spend a lot of effort to improve the stability of the database. And I have seen a lot of use cases in production. People have more than 500 terabytes data, or even more than 1 petabytes data in single cluster.
Yeah.
And so actually stores such an amount of data in the cluster is one thing. The stability of the cluster is another thing. You will not know what is issue there before you actually have a cluster in that scale in production. So we are confident that TiDB can run very stable in the production with those kind of data volume. And so that's why we spend a lot of effort to test database to improve the stability. And we have a tool called Killsmesh. It's Kills engineering platform inspired by the Kills Monkey from Netflix and also the Gibson test. And we designed a tool that can ingest failure into the system, no matter it's network failure, disk failure, or other things. You can name it. And then we can design some test case and try to evaluate whether TiDB is still stable or cracked under those failure. And we also have a lot of tests around that in our CI. We spend huge amount of effort to make the cluster stable. And I think compared with compared to other product, probably TiDB is more stable, and the stability for database probably the top priority for the infra engineers. So for me, I'm confident that TiDB is more stable and more scalable compared with competitors.
Interesting. Cool. Before we end this amazing session, I have one last question. What is the use case where you think TiDB would not be a great choice?
Yeah, we take a relational database, a general purpose database, and we have a distributed architecture. And there's still some cases that we think is probably not a good use case. For example, if your data volume is pretty small and you do not care about the reliability, a single database may be a better choice. And there's maybe the time series data, stored logs in the database. I still see some use cases like that, but probably the time series data, its databases are better choice for that kind of workload. And there's also maybe heavy analytical workload, and there's the concurrency also not high. So I think that's a use case for data warehouses. Yeah. And probably there's also some workload require extreme low latency, 1 or 2 millisecond latency. That's probably a use case for cache for Red.
Interesting. Yeah, that does make sense. While TiDB gives you a good mix of analytical and transactional use cases, there are of course some use cases that requires even more specialized systems that are built for those use cases. So great. I think this has been really insightful. I have some more pointers to go back and learn about TiDB because there are some interesting concepts in there. Unfortunately, because we can't cover everything within 1 hour, so we have to end this session here. But I'm also interested in doing another session because chaos mesh sounds like a very interesting thing. How it can be used to test databases. We can surely plan that. But yeah, anyone from our viewers, if they are struggling with the MySQL cluster, or they are trying to move away to a more scalable and reliable system, TiDB is a great choice. And it's open source, so you can read more on that. You can contribute to the community. And yeah, so if this episode has been helpful, please hit the like button and subscribe to the channel. Also look at the offerings of PingCap and also connect and ask questions to Lee if you have any for related to TiDB or PingCap, right? Yeah, thanks a lot, Lee. And it was really amazing to have you. Looking forward to more collaboration in the future.
Yeah, thanks, KV.